Good evening, everyone, and I hope you can all hear me. My name is Scott Taylor, and I'm a member of the IMechE Teesside committee. Welcome to our latest Tech Talk webinar. Also, the president of IPowerE Engineers, and I'm delighted that the IMechE and IPowerE are co-hosting this webinar. I hope everyone is safe and well in the current circumstances, and I thank you all for registering for the event and taking the time to join the webinar this evening. The topic tonight is net zero, real ones. By that I mean real gigascale projects in energy and industrial clusters. Based in Teesside, I work for Sembcorp Energy at the Wilton International site. I'm proud to say that both speakers tonight are leading Teesside-centric projects. Just some housekeeping. Each presenter will talk for around 20 minutes, followed by 10 minutes of Q&A. You can enter questions anytime in the Q&A panel down in the bottom right-hand corner of your webinar screen. Later, we'll hear from Colin McGill on net zero Teesside, but first, it's David Few of Innogy on their Sofia Offshore Wind Farm project. Over to you, David. Thank you.
Thanks very much, Scott. Just can you check that you can hear me okay?
Yes, thank you, David.
Perfect. So could I have the first slide, please? The slides are not coming up on my screen. Are they? Is it just a lag I'm getting, or?
Yeah, they must just be coming up now.
Okay, well, welcome everybody. My name is David Few. I'm the project director for the Sofia Offshore Wind Farm. I'm a civil engineer by profession, about 30 years experience in both in transport and in the wind or in the energy sector generally, but most recently in the wind sector. And very pleased to be asked to present to you tonight and describe some aspects of the Sofia Offshore Wind Farm. The next slide, please. I think I can move them actually. Let me try that. There we go. Before I get into talking about Sofia specifically, I should give you a little bit of information around Innogy and E.ON and RWE renewables, and the three sort of get used together at the moment for a good reason. Last September, E.ON was a sort of complex transaction, but E.ON Climate Renewables was taken over by RWE renewables as part of that transaction, and the second part of that will be that Innogy renewables will also be absorbed within the RWE renewables banner. So sometime later this year, probably by September, the E.ON Climate Renewables business and the Innogy Renewables business will all become as one as RWE Renewables and be renamed as such. Nonetheless, I'll talk about Sofia, and currently it's 100% owned by Innogy, and that's just a bit of background corporate level that you may have seen in the press. So a bit about Innogy. We're a diversified business. I'm just really going to focus on the renewables part of it. So we've got a 3.6 gigawatt portfolio, mostly focused on Europe. There are some smaller projects in the wider, more globally, but just focusing on Europe. 3.6 gigawatt portfolio, 6.3 gigawatts in development. We were the first mover in the UK waters, so back with North Oil in 2004, first one to build an offshore wind farm in the UK waters. Over and above that, of that 6.3 gigawatt development portfolio, 1.4 gigawatts is under construction. You can see on the slide there the split there. So we're into both onshore wind, offshore wind, and hydro. So 30-odd% is on offshore wind at the moment, but that's going to change quite dramatically in the next couple of years. So just look at our offshore fleet, and this is pictures of all of the farms which Innogy either fully own or are a large shareholder in. So over in the sort of Irish Sea there, off the coast of North Wales, we've got 3 farms quite close together: Real Flats, North Hoyle, and Gwynty Moor. At the time, Gwynty Moor, I think, was probably the biggest offshore wind farm in the world at 576 megawatts. But as you'll see later on, we've upped the scale of that. Over on the east coast, 2 projects there in operation. So Greater Gabbard at 503 megawatts, and Galloper, which was completed in 2017, 2018, 350 megawatts. The Triton Knoll project, which is currently under construction, that's 857 megawatts. And you can see there, that's one of the picture is one of the offshore substations. There's two offshore substations on that farm. It's an AC system. And then up at the top, you can see that's where Sofia is, out almost in the middle of the North Sea. And that will be a 1400 megawatt farm when it's complete. So offshore wind has evolved. A little bit of a diagram there. Won't dwell on that too long. So left to right here, this is sort of the evolution of Innogy's wind farm portfolio, starting with North Hoyle at the left. So at the time, a big endeavour, 60 megawatts, 7 kilometres offshore. And I won't go through them all, but as you can see right across on the right-hand side, we've been moving further offshore and or into deeper waters. So Sofia itself is 1400 megawatts, 21 to 36 meters of water, and 195 kilometers offshore. It's about 90 kilometers inside the sort of dividing halfway line across the North Sea. So it's by far the largest project in Innogy's portfolio. It was developed as part of what was called the 4Wind Consortium. It was 4 owners, so SSE, Statkraft, Statoil, Equinor, and ourselves as Innogy. And since 2017, Innogy's taken full ownership of the Sofia farm. Haven't been developing it since then. We won a contract for difference in the 2019 auction, which was great news, great boost for the project team and for the company, and hopefully for the UK. That's a price of £39.65. So as part of that evolution, wasn't too many years ago, probably 5-6 years ago, the prices were in the 150 odd pound a megawatt hour range. It was quite a surprise in the 2015 auction when they were 57.50 and 74 pounds per megawatt hour. But here we are, 39.65 for this delivery year. Overall, it's about a £3 billion investment in capex, and we're planning to make a final investment decision in early 2021. All the consents are in place for it, with still 1 or 2 pieces of sort of onshore planning permissions we're going to apply for, but generally speaking, there's consent there for the whole farm to be delivered and developed. So our next steps through this period through to early 21 are for us to carry on the development, continue with our design, continue with our procurement and secure all of our bidders for the project, arrange the project financing, and reach a final investment decision with the company. So this picture of where it is. So as I say, a long way out in the North Sea, and it's a sort of almost rectangular shaped farm. And there's three others on Dogger Bank which have also got consent at the time. So the other, well, there's now 2 owners of what was the 4Wind Consortium. They're labelling themselves Dogger Bank Wind Farms, and they own the other three farms there, which are surprisingly enough called Dogger Bank A, B, and C. Sofia is the furthest offshore of the 4 of the farms. So it's a large site large site anyway, but also by comparison with other wind farm sites. It's 593 kilometres squared, which is roughly the size of the Isle of Man. So we've got consent for up to 1400 megawatts and for up to 200 turbines. And this farm was consented back in 2015. So at the time, we'd have probably needed to put all 200 in there, but we won't actually need quite that many now. I'll come on to some details about the turbines in a bit. We're consented up to a maximum elevation of 315 metres, which is round about the same height as the Eiffel Tower. So you can just picture somewhere between 1 and 200 Eiffel Towers size structures in the middle of the North Sea. It's quite an incredible endeavour. Also consented up to a rotor diameter of 288 metres. So just to get that in to context, that's 2 blades of 144 metres, or up to 144 metres. They won't actually be that long, but well over 100 metres in length, and made of fiberglass and balsa wood. Quite incredible things, each weighing 50 tonnes. The water depth, as I mentioned earlier, is 21 to 36 metres, so that varies across the Dogger Bank site. But on our export cable route, which is 208 kilometres long, we go up to 80 metres deep. So that's quite a difficult, and roughly half of that is in rock. So we will need, that's quite a challenge to put that cable in. The landfall is between Redcar and Marske by the Sea and Teesside, and on land it goes about 6.8 kilometres into the Wilton site, which is owned by Semcor, where Scott works. And there's a converter station there, and then another 2 kilometres onto the grid connection, national grid connection at Lackenby on Teesside. When it's fully operational in roughly 2026, or progressively from 2025 onwards to 2026, it'll have produce enough electricity to feed approximately 1.2 million average UK homes with their electricity needs. So just a graphic of the timeline. So 2019, September 2019, we won the contract for different auction. It's probably worth bearing in mind that the project had been sort of first conceived nearly 10 years before that, so 2009, and the first thought of putting some wind farms on Dogger Bank. And then through 2011, that's when the Innogy, with its partners at that time, finally sort of really got going on the development of it. And it's taken through till I joined the project in 2018, but the project team was established just at the end of 2017. So it's a long haul, so almost 15 years in total from end to end to get consent, get the development done, and ultimately the construction. I hope to make a final investment decision in early part of next year and start construction pretty much the same time. On offshore, so during that period 2021 to 23, we will be doing fabrications for the offshore components, so the foundations, the turbines, and so forth. And then the first generation, pretty much right at the end of Q3 2024, and that will then carry on through till early 26 when we'll be fully operational. Just a schematic of the farm, or the components. So we have wind turbines, and it's obviously not to scale. The wind turbines sit on foundations, and in our case there will be monopile foundations. They connect at 66 kilovolts through to a converter platform, and that will convert the AC electricity from the turbines into DC. We'll then transmit that through the export cable to a joint bay just onshore. There'll be an onshore cable, which again in DC, to another converter station, which will convert it back to AC. And then there is a section of further AC cable through to the national grid substation, and that then connects into the main part of the national grid. So now I'm going to talk through the various components of the farm. Sort of five main components, so a few slides on each and a few technical details. So the turbines are 3-bladed horizontal axis turbines, design life of 25 years. In letting the contracts for these, there are two elements to that. One is turbine supply, so the TSA, the turbine supply agreement, and the other is the service and maintenance agreement. So generally speaking, the first 5 years or so of a contract, you'll have a service and maintenance agreement with the original equipment manufacturer. And at the moment with Sofia, we are working with that preferred supplier. So we're just finalising the agreements for that, and then the announcement for that will be in the next few weeks of who's going to be providing those turbines. And I've also put on these slides just some indication of what the supply chain opportunities, because this will be hopefully an economic benefit to the UK, but also hopefully to the North East in particular. So I've got some slides, some details there. Generally speaking, most of the procurement will be done with 5 large tier 1 suppliers, and they then will have a supply chain which they'll develop, some of which is fixed as part of their normal business, and some of it, particularly the local stuff, will come as they develop their contracting strategy once they've been appointed as a preferred bidder. So in terms of the turbines, a bit more sort of technical detail there. That's not a picture of any specific turbine that we're going to be using. So there'll be over 100 of them on Sofia Farm. The rotor diameter will be over 220 meters in total. So that's 220 meter diameter. Power will be at least 12 megawatts. So that's probably the smallest of the ones on the market now for offshore. You could obviously buy smaller ones should you wish to, but because there are some legacy ones around, but the state of the art is now above 12 megawatts. The hub height is roughly 140 meters, and part of the reason for choosing that is to get the optimum position in terms of the wind, but it also impacts on things like the wave run up and the ecological conditions of bird flight paths and so forth. So you want the hub height sort of optimized in terms of where it should be. Rotational speed. Well, the question often asked is what's the speed at the end of the blade? So roughly 180 miles an hour, 90 meters a second. And the piece on the top there, that tower head mass, so the nacelle with the blades, is around 800 to 900 tons in total. In terms of voltage, it's a as I mentioned earlier, 66 kilovolt system that comes out of the turbine. So the cable is going to the converter station, 66 kilovolts. And in terms of wind speeds, it's designed for a 10-minute mean speed of 50 meters per second, so 100 miles an hour. So you probably can't quite conceive of being out in the middle of the North Sea in 100 mile an hour wind, but this is what these are designed to take. Moving on to the foundations. So the foundations are generally speaking in two parts. So you have a monopile. There are other ways of putting offshore turbines in place, and the most common one is a jacket structure. So a tripod or either 3 or 4-legged jacket structure. Because of the water depth and the soil conditions at Dogger Bank, that makes it suitable for a monopile. So these are large steel tubes, somewhere in the region for this farm, 8 to 9 meters diameter, with a length up to 80 meters, and the embedment there is of roughly 40 meters. So you've got 40 odd meters under the seabed, between 25 and 37 meters underwater, and then some above water level. On top of that, you put a what's called a transition piece. This is about 250 tons, and that's where you pile the main monopile in. You then bolt the transition piece to that, and the transition piece carries things like platforms and ladders, and in some cases the electrical equipment. Always has a platform as a laydown area and a sort of working platform at which point the tower which the turbine is attached to is joined onto the top of the transition piece. We are looking at variant design, so in some cases that's been done as a single unit, so a monopile and transition piece combined, and we're having a look at that still. In terms of corrosion protection, to last 25 years, so the atmospheric zone, there are coatings on it. In the splash zone, we have coatings plus a corrosion allowance, and in the submerged zone, we have both those coatings and what's called an impressed current cathodic protection. So this is a slightly sort of state-of-the-art version, really, of putting lumps of zinc on the steelwork, but it uses an electric current to achieve the same end. So what we've got here is very much state-of-the-art technology, very large and extreme fatigue loads, because the fatigue loads scale by rotor area. In fact, all the loads scale by rotor area. We've got high wave loads and very complex geotechnical conditions, which I'll come on and describe a little bit later. And the other main challenge here with the foundations is the distance from shore and the logistics of putting that in, as well as the weather of being in the North Sea, middle of the North Sea. just a little bit about the sort of cost breakdown. Primary steel work, which is the monopile and the transition piece, is roughly 2/3 of the overall cost. Then we've got all of the add-ons, so the platforms, ladders, and so forth, which add roughly 1/4 of the cost. And then you've got coatings and various miscellaneous items, which add up to the total cost of the foundations. Onto the electrical system. As I mentioned, this is we've gone for a high voltage DC system. It'll operate at 320 kilovolts in DC. We did feed studies from this through 2018 and into 2019, and we're now at the point working to finalise agreements with a preferred supplier, which we'll be announcing in the next few weeks. The supply chain opportunities for the electrical system are on the onshore civil works, electrical installation, plant hire, and various miscellaneous items. A little bit about the technicalities for the DC system. So it's a point-to-point cable. It's shown as 2 cables there, and there will be 2 cables. There's no redundancy in that. It's a simple DC circuit, so 2 cables making up the overall circuit. So you have an inverter and a rectifier from the receiving end, from the sending end at the offshore converter station to the receiving end at the onshore converter station. Question of why choose DC. At the time when the decision was made to go with that, this graph really shows the trade-off between distance and cost. So for an AC system, which is the orange coloured line, you have a basic cost of the stations, so the substation offshore and the substation onshore, and then you've got a cable cost, which increases obviously almost linearly with length. You then got, if you look at DC, you have a much higher cost of the converter stations because they're bigger. So the converter station for the offshore converter station is well over 10,000 tonnes for Sofia. You then got a sort of more modest cost per metre for the cables. So they do you do have a break-even point. And for submarine cables, that's somewhere in the region of 50 to 80 kilometres. And the technology, particularly for AC, has evolved over the years. So I don't have the figures to know exactly what the break-even point is now, but certainly at over 200 kilometres away, DC was deemed to be, at the time, the best solution. There's also a consenting aspect to it, that when the project was consented, it wasn't even conceivable that you could do it in AC. So you'd have needed and you still would, you'd need a rectifier platform roughly halfway out to the wind farm. That wasn't consented, so the possibility of sort of switching back to AC wasn't really there. It had to be a DC system. The cables, so 2 sorts of cables. There's what's called the inter-array cables, and these connect up the various turbines in the farm, either in sort of single lines or in loops. And in total, we'll have roughly 370 kilometres of inter-array cable, and that's 66 kilovolts AC 3-phase with 3 cores. And along with those 3 cores, we will have a fibre optic communications cable to link to each of the turbines for control system purposes. On the DC side, the export cable there is essentially a single piece of copper, and there's 208 kilometre lengths of that. So as I say, that's not it's not a redundant system. That's just two cables which make up the circuit. For both of these packages of work, we've been out to tender, done initial engineering and installation studies. We've been out to tender, and we're going to be choosing our preferred suppliers for that towards the end of this year. Since many of you may live in the northeast, you might be interested in the onshore route. So that comes from Marsk by sea through, and it's a total of 6.8 kilometres onshore. Passes through sort of 12 pieces of land before we get onto the Semcor site, the Semcor Wilton site. It's all farmland. It does skirt around some houses towards the sea, but it's all in all in farmland, and relatively simple compared to most offshore wind farms. The connection, some of those are 50-60 kilometres. Ours is only 6.8 through to the Wilton site. I should probably just say the landfall where we go under roads or under railways, and also to get ourselves through the nearshore area, we'll use a horizontal directional drive, so a sort of percussion instrument to take the cables through those locations. So no sort of open cuts under roads and railways. Site investigations. This is a piece of work that's actually carrying on at the moment. So Dogger Bank, in terms of its history, as a sort of more geological history, it was Doggerland as recently as 10,000 years ago, and provided a land bridge to Europe from the UK. So it's the largest site investigation Innogy's ever done for an offshore wind farm. And you can see by the picture there, hopefully it's a pretty complex ground, lots of different lenses and inclusions of materials, of different materials, and partly because it's a very large site, it's also quite complex. So the turbines will be roughly 2 kilometres apart. So in a 2 kilometre distance, you get quite a significant difference between the ground conditions. So consequently, we need to do quite an extensive site investigation. Certainly at every turbine location, we'll be doing either boreholes or CPTs. We're also surveying with geophysical and geotechnical measures the export cable routes, the array cable routes. In total, 7 vessels are undertaking that investigation, both geotechnical, geophysical, as well as some environmental studies, so benthic ecology and so forth, and some of that's up to 70 metres deep to the seafloor. So a complex and time-consuming activity. Fugro will be doing that work for us. They started in February, and we had probably the worst possible weather for that. Weather that time we had 2 hurricanes within the first fortnight. Yeah, not ideal conditions to start it, but that will carry on and finish up in July. I think we've run out of slides 3 short. There we go. So yeah, site investigations. Fugro have been doing this work. That's both physical investigations as well as almost as we go evaluation of the results to determine what further investigations we should do. So there's a basic program of work, and then we tailor that as we go. Just sort of that's the end of sort of the main part of the presentation. So just revisit what are the next steps between now and early part of next year. We'll be finalising the procurement of all the packages, completing some design work, getting the financing in place, and then get ready to start construction at the end of early part of next year. Any questions? I probably should just point out we have a Sofia website, so sofiawindfarm.com. You can also find that through the Innogy.com website. So happy to take any questions.
Great. Well, first of all, thank you very much for that presentation on Sofia Offshore Wind Farm. Very interesting. The most popular question was, why out at Dogger Bank? Why is it so far out in the North Sea? Is that to avoid shipping routes? Is it windier? Why that particular location?
Well, Dogger Bank is a pretty good location to build it because, as you've seen there, the depth of the sea between land and between the sort of mainland and Dogger Bank goes up to 80 odd metres deep. The cost of foundations grows certainly by square rule, but or maybe even cubic rule as you go deeper and deeper. The limit of monopiles at the moment is around about the 40-metre water depth mark, but that does depend upon the soil conditions. So it's a pretty good location to build it from a geotechnical point of view because well, the water's the right sort of depth. The ground conditions, whilst they're complex, they're not particularly difficult. It's sands and clays, mostly, as well as some boulders. But the other thing is it's pretty much right in the middle of the North Sea, so you get an absolutely great wind resource. Nice constant winds and also pretty high winds, which not ideal in terms of structurally, but if you're going to build something that's can withstand 100 miles an hour winds, then you might as well put it in a place where the wind conditions are good for a good part of the year.
Thanks. So sounds great location for all those things. What will you do to minimise the impact on marine life with the construction of the wind farm?
Well, within the consents there are fairly obviously great constraints on that. So in terms of marine life, this is in an area which is designated as a special, as an example, and there are many conditions on this that we have to fulfil. But this is an area designated as a candidate site for a special conservation for harbour porpoise. So exactly what the arrangements will make to deal with that, clearly there are constraints that we have to fulfil. But what the exact plan is, that will be determined as we sort of finalise the design, finalise the installation methodology, and then work with installation contractors to make sure we're fulfilling those consents and minimising the impact.
Thanks. And with the proliferation of offshore wind farms in the North Sea, what safety considerations is there for one of the busiest shipping channels in the world?
Dogger Bank's not a particularly busy shipping lane because of its shallow or relatively shallow. It actually has quite sort of complex currents that go over it, so it's not the perfect place to go for large shipping to cross. It's an active fishing zone. That's one thing. So in terms of safety, there was 2 or 3 aspects to that. One is in terms of sort of search and rescue, in case, because we will have people on these turbines, not all of the time, but certainly through the summer doing maintenance as a regular program of maintenance. So we have a need for search and rescue capability there, and so the turbines are pretty much arranged in straight lines so that you can fly helicopters down the paths between them. In terms of the sort of other aspects, shipping safety is one thing. Clearly they're pretty big, so and you've actually only got a small cylindrical part going into the sea, so and given the size of the North Sea, they're a pretty low risk of impact on the turbines. The other aspect is obviously construction safety, which is a very key consideration in terms of how we design it and how we arrange with the contractors to install it to make sure it's as safe as it possibly can be during that construction period.
Thanks. Two final questions, I think, David. Hopefully, firstly, will there be any opportunity for Teesside to be involved on the onshore construction and the future ongoing operation and maintenance of the wind farm?
So there's 2 parts there. One is in terms of onshore construction. There's a couple of packages of work will be coming out for tender. One in a couple of months' time, and then another one early part of next year for the onshore cable works. So most certainly, moreover, there are opportunities within the supply chain to supply components. So for the main manufactured parts, so that's certainly an opportunity there. We've got a supplier portal which we've got several hundred local companies that have registered on now, and early part of next year we'll be having Meet the Buyer events. They would have been this year if we'd apart from the current conditions. So early part of next year we'll be holding those where the tier 1 suppliers, the main contractors, will be introduced to sort of local suppliers who can potentially contribute to their supply.
Thanks. And
so there's 2 parts to that question, Scott.
Very well. So that was kind of one question in 2 parts. Apologies. And the next one, probably another question in 2 parts as well. Is there any planned upgrades after the CFD or the design life of the project, and how recyclable are the components that the wind farm is constructed of?
In terms of planned upgrades, The farm life is designated as, or design life is 25 years. It's just about conceivable you could replant it, because our license with the Crown Estate runs for 50 years. So you could just about replant it at that point. That would probably involve taking out the foundation, or taking the turbine off and putting new foundation, because I would assume that in 25 years' time the technology will have moved on, even from where we're at today. So you'll probably be looking at removing it, but using the site again. And in terms of upgrades to it, there's a degree of optimization that will carry on between now and when we finally install it and put it in place. Beyond that, operational sort of optimizations will carry on about how it's operated and maintained. In terms of, is it recyclable? Well, pretty much all of it is steel. So yeah, eminently recyclable. Within the consents and the licenses, you have to have a decommissioning plan, and you have to reserve monies to do the decommissioning. So that's all covered within the overall project budget. So there's sort of no question of getting to the end of the 25-year design life and just walking away and leaving still in the North Sea.
Well, that's great to hear. David, thanks again for a great presentation and very comprehensive answering of all the questions. Sorry we couldn't ask them all. There was plenty of questions. Hopefully I've covered the general topics that people were asking about. So thanks, David. I would now like to hand over to Colin McGill on the Net Zero Teesside project. Over to you, Colin. Thank you.
Thanks so much, Scott. My name is Colin McGill. I work for BP. I should say at the front, I'm not an engineer. I'm a theoretical physicist by background. So if you ask me detailed engineering questions, I'll either pass or bluff, and you have to decide which I'm doing. But the work we're doing on Net Zero Teesside is funded at the moment by ODCI, the Oil and Gas Climate Initiative, which is started by a group of the CEOs. So Bob Dudley, the CEO of BP, got together with a bunch of the other CEOs, and they decided that they wanted to do something about climate change. And it was launched in 2014, and up to now, last year, it had its 12th member, and it's a mixture of international oil companies and national oil companies. So you've got Saudi Aramco in there and Petrobras, for example. And there are two parts to ODCI. The first part is a sort of policy part. It's aimed at working with governments and other stakeholders to see if it can create policies to help with climate change. And the second is an investment fund of over $1 billion. And it's not a classical investment fund in that it's not looking for an investment return. Its mission is to stimulate a market in carbon capture, utilisation and storage of over 1 billion tonnes a year. It's got a life of 10 years, and over that 10 years, it's designed to stimulate. So its mission is to try and choose technologies, give them some feed capital, get them working, and then hopefully they'll scale up without further investment. With £1 billion, it sounds like a lot, but obviously it's not going to do much in terms of storing 1 billion tonnes of storage per year. So it really is about stimulating that market. And the Net Zero Teesside project is the first project that that ODCI picked up. So I think that Net Zero Teesside is actually one of the most critical projects for climate change. Well, not just Net Zero Teesside, but all the projects that are being looked at in the UK. And the reason for that is, first of all, carbon capture, utilisation and storage is absolutely required to meet climate targets. I don't think I've seen a single legitimate study which says you can meet those without some form of carbon capture and storage. So for the IPCC, for example, the Intergovernment Panel on Climate Change, they estimate somewhere between 5 and 10 billion tonnes a year of CCUS is required by 2050 to reach the Paris goal of 2 degrees centigrade. And if you want to go to 1.5, it requires even more and even sooner. Now, one of the things that we've been working on is trying to work out what the business models will be. So if you invest in carbon capture and storage, how do you actually get a financial return on that? And if you look at where carbon capture and storage projects in the past have failed, it's fundamentally because of lack of government support. So if we can get these business models in place, not only it will unlock net zero Teesside and similar projects, but it'll allow them to be applied at scale. And if you look at the UK's also got a proud history of developing regimes which have then been exported to other jurisdictions. And the contract for difference is a great example of that. That's what the UK has used to enable low carbon power, as you've just heard, for offshore wind. If we got that in place for CCUS, I think those models would then be adopted elsewhere. So this time last year, the UK committed to become the world's first country to become net zero by 2050. And as a result of that, in just 1 year, over half of the world's GDP has plans to get to net zero by 2050. So if we can get these business models in place, they'll have to be picked up by the other countries. There's no way really for them to reach their targets without similar models. And for those of us working in the oil and gas industry, if half the world's GDP is going to be net zero by 2050, we're not going to be selling many products unless we can actually decarbonise those. So it's important to the oil industry as well as the society at large. So what is the energy system going to look like by 2050? So this is a slide from the Committee on Climate Change. I suspect most of you know what that is. It's a government body. It's not part of government, but it's set up by government. And their mission is to tell Parliament how they should, what policies and what things they need to do to meet our requirements on climate change. And they were the body that recommended that we should adopt net zero by 2050. Now, this is a table taken from the report that they issued at the time, and it's looking at the energy system in the UK. And fundamentally, what they're saying is that the energy usage is going to double, electricity usage rather, is going to double between now and 2050. That's partly for electric vehicles and partly for hybrid heat pumps to do heating at home. Most of that will be supplied from renewables like low carbon, like offshore wind that David was speaking about. There'll also be a requirement for hydrogen, and there are two reasons for that. One is for using in industry as an alternative to using methane for heat sources. And secondly, there's a possibility that that could also be used to heat homes instead of methane. Now, at the moment, there is the cheapest way of producing hydrogen is to reform methane, and that requires you to take the CO2 out of the methane, convert it to hydrogen, but then you need to store the CO2. Now, there will be at some point some excess wind, and so some of that will get captured from excess wind through an electrolyzer and fed into the system. But the baseload hydrogen is going to be largely from converting methane into hydrogen, at least at the moment, unless the cost of offshore wind drops dramatically. And finally, there's a third component of that, which is carbon capture and storage. You've got to take the CO2 that's generated and store that. So we've talked about the hydrogen, but there's also a requirement for gas-fired power generation. And the fundamental reason for that is that you can't rely on the wind. Wind power is fantastic. We need a lot of it in the system, but there are times when it's just not windy. So in this month, for example, I think there have been about 15 or 16 days where you've had a sort of wind drought in May. So you need a backup so that you can actually have electricity as you start to, as you rely on more and more renewables. And if you have that, you want to take the CO2 from that and store it somewhere offshore to keep it safe. And so if you look at the proposed breakdown of that, you've got hydrogen production, you've got CO2 from gas-fired power stations, you've also got about 50 million tonnes from BECCS and biofuel. So it's quite hard to reach net zero unless you've got some negative emissions. So if you capture CO2 that's emitted as part of a renewable process like bioenergy and inject that underground, that gives you negative emissions. And that stops you having to pay for very expensive means of decarbonising things which are otherwise very hard to decarbonise. And finally, there's about 24 million tonnes of CO2 from various industrial processes that will also need to be captured and stored. So if you look at the total hydrocarbon use there, it is basically saying there's very little oil demand in the UK because we'll all be using electric vehicles by then. But natural gas demand will still be there, but lower than today's use, about 3/4 of today's use. And if those of you who have been listening to Chris Stark, the CEO of the Committee of Climate Change, what he's been saying is he's looking at, this is just one model of how we might get there. This was intended to demonstrate that the path to net zero by 2050 is feasible, but he's looking at alternative scenarios now, which may use significantly less gas than this. Although he's also said that when they try to do that, it keeps costing more. So it looks like there will still be a requirement for quite a lot of gas use in the UK if we're to meet net zero as cost efficiently as possible. Now, the conditions for carbon capture and storage in the UK are very positive and the most positive they've ever been. So first of all, in May last year, we committed to achieve net zero by 2050. Secondly, in the budget just about 6 or 7 weeks ago, although it seems a lot longer, the UK committed to spend 800 million in CCUS projects in the UK. And that was actually mentioned in the budget statement, but what you may not have seen is in the Red Book, which supports the budget, there's also included support for a gas-fired power station with CCS, supported by consumer subsidies, which again is the contract for difference model that David talked about earlier. It's also important that the places where sort of carbon capture hubs are being looked at are all in industrial regions. And so doing carbon capture in those areas supports the Conservatives' levelling up agenda for the UK. And perhaps more interestingly than that, one of the questions I've been asked very frequently over the last sort of 7 or 8 weeks is, well, will the government actually have any money to spend on projects like this after the COVID pandemic? But the consistent message we're getting back is it's going to be even more important. They realise that coming out of COVID, the economy is going to be in relatively poor shape. And so by spending in infrastructure, that's a way we can actually kickstart the economy. And so if anything, they're more interested in projects like Net Zero Teesside than they were in the past. And we've heard, for example, that the Northern Powerhouse team is looking exclusively at a green recovery post-COVID and is going to be looking to implement that as quickly as possible. So what about Net Zero Teesside? What actually is the project? Well, first of all, it might be worth talking about why Teesside was chosen. The Oil and Gas Climate Initiative looked at over 55 locations in the UK before deciding on Teesside. And in retrospect, they didn't choose it quite for these reasons, but there's some very good reasons why this works so well here. The first is it's a compact site. Obviously, it's sort of an ex-ICI chemical site, and it's relatively compact, which makes it very straightforward to build a gathering system which works. Secondly, it's in one local authority, which means that there's very strong local political support, but there's also very strong industrial support. There's a group of industries that have been trying to decarbonise in Teesside for a number of years, and they've kept going despite consistent setbacks from the government over carbon capture and storage policy, and that's fantastic. So 2 of those, for example, are on here. You've got CF Fertilisers and BOC. CF Fertilisers produces food-grade quality CO2 as a byproduct of its process, and BOC, in converting hydrogen from methane, again produces not quite pure CO2, but very high concentrations of CO2 in the flue gas, which again makes it very cost-effective to decarbonise. So you've got something like 750,000 tonnes of low-cost CO2 to be decarbonised there already, which is pretty great. The other interesting thing about Teesside is if you look at the net emissions from Teesside, the recordable emissions are somewhere between 3 and 3.5 million tonnes a year. So recordable emissions are things which are reported to the EU ETS, and people have to pay a carbon tax. But there's also about 3 million tonnes of non-recordable emissions. So CO2, which is generated from renewable processes like energy from waste and bioenergy. And if you capture the CO2 from that, that actually generates negative storage. And that's what's so interesting about Teesside. It allows you to actually get to net zero because of the fact there's so much renewable energy there. Now, finally, there is actually a little bit of spare capacity in the hydrogen plant in BOC. There's also a hydrogen distribution system there. And so it's also possible we could experiment with fuel switching in some of the industries in Teesside. It's going to be the most efficient, cost-effective way of doing that, I believe, in the entire UK. So that's another sort of reason why Teesside is interesting. And finally, we plan to underpin all this by a new gas-fired power station with CCUS. Now, part of the reason for that is that that's actually required by the UK energy system, and I'll touch on that in a couple of slides' time. But it's also there for the investment purposes. So it's hard to be certain if you're planning on infrastructure for 20 years. It's hard to be certain about which industries will still be there in 20 years' time. However, if you can get a contract for difference of 15 or 20 years, that gives you a lot of certainty that any infrastructure will be used and that money will be coming in. So it helps give confidence to the investors that we can actually go forward. So if all this is successful, we can do a number of really exciting things in Teesside. We can create the world's first decarbonised industrial hub, and that could be as soon as 2030. And that's, as I said, largely a result of the 3 million tonnes of renewable CO2 that's generated every year there. We'll also be able to create the world's first dispatchable low-carbon power. So the way that you capture the CO2 is with an amine plant. Now, an amine plant is a large chemical plant. It's designed to operate 24/7. It's not designed to actually be turned on and off. But we've been doing a lot of work on that, and we're pretty comfortable now that actually it's possible to do that. So you can run this in a two-shift system, so you can turn off the power during the night when it's not required because there's plenty of spare capacity, and then turn it on during the day when you do need it, and also at times when there's not enough wind or solar to power the grid. So we're becoming increasingly confident we can do that. And finally, it can be the world's first negative carbon electricity. And again, that helps balance the system that the UK will need. It'll lead to negative emissions in order to be able to meet net zero. So it's a really exciting place to try out decarbonisation. So as I mentioned, we've been looking at the UK power market and trying to understand about what's the most effective, cost-effective way of decarbonising that. So if you look at the black line on the right, that is the carbon intensity of the grid. And the reason it's sort of wiggly at the beginning is it's kind of based on, we went to a company called Baringa who specialises in modelling the power market in the UK. And the bit at the beginning is based on known investments that are coming through. But once you get to about 2030, that we don't quite know what that's going to be. And so what we've asked them to do is just assume that from 2030 to 2050, the carbon intensity of the grid declines linearly over time so that by 2050, it gets to zero. And we then asked them to look at, if you do that, what's the most cost-effective way of generating power? And we've also asked them to look at not just one scenario, but a huge range of scenarios reflecting different assumptions on gas price, on nuclear, on renewables cost, etc. And what you're seeing here is a sort of typical representation of what comes out. So first of all, you can see that in green, that there's a big expansion of offshore wind. There's also a big expansion in the total amount of power required, as I mentioned earlier. You can also see that the unabated gas, which is just labeled the CCGT, that's sort of, I don't know what quite colour that is, but sort of dark purple, that declines from now and starts dropping off from 2030, and that's replaced by abated CCGT, which is gas with CCS. And finally, from about 2040, you start to see hydrogen being important there. And so what's going on there is you're having a number of peaking plants, and those peaking plants are typical open cycle, and it's much harder to capture the CCS from them. You're only running them for maybe a few hours a year, and it's just not cost effective to put carbon capture on there. So when you start to get to really low levels of carbon in the grid, you're better to produce more hydrogen and then burn the hydrogen in your plant. When you're running the CCGT plants for a significant period of the day with a high load factor, then you're better off capturing the CCUS and building a post-combustion capture plant on it. And so as we looked at these, we found some interesting facts. So one of the things we found is that reducing the cost of wind doesn't actually increase the optimum amount of wind on the system. And the reason for that is that once you've installed a certain amount of wind capacity, if it's windy, you can use all that capacity. And building more doesn't help you in the times when you have wind. However, when it's not windy, you need backups for those. Of course, reducing the cost of offshore wind is great because it reduces the total cost of the system, but it doesn't change the capacity of that system at all. And likewise, nuclear, because nuclear is so much more expensive than any of the other forms of power, the only time nuclear actually starts to play more significant role in this is when you've got very high gas prices and very low nuclear prices. And any other configuration, actually you're better off with gas with CCS rather than gas-fired power with CCS, as opposed to nuclear. So we're starting to get some very interesting insights about how the power market develops. In the near future, we're hoping to be able to publish this analysis so that people can actually read and start to understand what that will look like in the grid going forward. And then kind of finally, what's the future of this? So for a start, we are already in discussions with Humberside. Humberside, lots of industrial emissions there. And we also want to use the same store. So we're working together to see how we can do that collaboratively. And we also believe that once it's done at scale, that will unlock clusters there and also around the UK. If we can get this going in the UK, it's the potential for huge value added into the UK economy. So if you just go back to the economic impact of this, we used Vivid Economics to do an analysis for us about how much this would actually generate in Teesside. And just doing the project in Teesside would generate something like £400 or £500 million per year whilst the project is in construction. And it will generate something like 4,500 direct jobs, which will peak at 5,500 jobs as the project nears completion. But once that's in place and other projects kick off, development of that and deploying more CCUS clusters globally would actually generate up to £1.5 billion of added value in the UK and up to 18,000 jobs. And if you go beyond that still and start to export goods and services, that'll generate a further 1.2 billion and a further 13,000 jobs. So it's a great opportunity, not just in Teesside, but also for the rest of the UK to actually generate more value and more highly skilled jobs. And with that, thank you all very much. I hope you found it interesting, and I hope there are some interesting questions for me to answer too.
Colin, thank you very much for a very interesting introduction to Net Zero Teesside. We have some questions, of course. The first one, how many industrial emitters need to be on board for the Net Zero Teesside project to go ahead?
So we want as many emitters as possible. And so it's not a question of how many you need, it's really a question of how many of the government will actually put in relationship things in place to allow them to actually decarbonise cost effectively. If you speak to most of the emitters in Teesside, they are selling into a commodity market. Ammonia is a commodity product. So if they have to pay anything which allows them to increase their prices, they just won't be able to sell it, and they'll go out of business and will offshore the CO2 production somewhere else. So getting the right business model in place to allow them to decarbonise is what will allow them to do that. So if we just got BOC and CF, that would be pretty much all we'll need to make the project go. But actually, there are many more emitters who are very keen to do this if they can get the business models which will allow them to support decarbonising their product.
Thanks. In terms of the power station, what's the efficiency of a CCG plant with carbon capture compared to one without carbon capture?
So you lose about 15% of the power generation to do the carbon capture process, to heat the amine process. So about 15% parasitic load.
Thanks. And what about the power consumption of the booster compressor station to send the CO2 to the offshore storage?
So that's relatively small in comparison to the parasitic load. So I think we're talking about 10 megawatts to begin with, going up to 50 megawatts later on if you get up to 10 million tonnes per year. So it's relatively small.
Okay, thanks. And how is the CO2 transported out to the storage, offshore storage? Is it supercritical CO2, and how is it injected in and safely captured and stored in the North Sea?
You're correct. It is supercritical. So I'm sure many of you know, but CO2 is a very interesting fluid. Above about 1600 psi, it becomes supercritical. So that means it's got the density of a liquid, but the viscosity of a gas, which means it's a fantastic thing to actually transport and also to inject into a reservoir. So the idea is indeed to compress it up to supercritical, and then you pump it offshore. And at that point there, it's got enough pressure to actually be injected into an underground reservoir. The one we've chosen is called Endurance. It's a very large saline aquifer. It can deal with up to 500 million tonnes of CO2 in total over its life. So to give you some idea how long that will last for, we're anticipating that if Net Zero Teesside fulfills its potential, that could be up to about 10 million tonnes. So it's got about 50 years of capacity available to it just for Teesside. Although if we combine with Humberside, there will be less. We're also looking at other stores in the area. We've identified other stores. And what we plan to do is as it starts to get full, we would then actually expand that network and install CO2 elsewhere in the North Sea.
Thanks. Is there any thoughts of the carbon dioxide capture being utilised for some industrial process?
So lots of people are looking at that. So as I mentioned, the CF fertilizer, for example, produces CO2 as a byproduct, but it also has decided to refine that and make it food grade quality. So some of that CO2 gets shipped off into making beer and other fizzy drinks, and also crumpets and other things which use CO2. But there's a limit to how much of that you can do. There's a lot of research going on at CO2 utilization. So, for example, there's a company called Solidia, which has got a very interesting technique of as it makes paving slabs, and as it cures the paving slabs, it puts polytunnels over those, injects CO2 into those polytunnels, and the CO2 is absorbed into the cement. Now that's great, but it's actually a relatively small amount of CO2 you can use up that way. In order to get to the billions of tonnes a year that we're going to need to do, nobody's yet identified a way of utilising that much CO2. At the moment, it's relatively small.
I think it was so your timescale for the government supporting the project. When is that? When will you hear that CFD announcement or whatever you need in terms that you can progress the next stage?
So we are working very closely with the government at the moment on trying to get the business models in place, not just for us, but also for the for hydrogen, for industry, and for BECCS, in addition to the carbon capture and storage. And what they are telling us is that those business models will be in place by the end of the year, and they will publish those then. And then we plan to negotiate heads of terms with them by the end of one quarter, first quarter next year, and then we'll go into FEED sometime in the second quarter. If we go into FEED then, we will be looking to start execute in early 2023.
Great, thanks very much, Colin. I think that's all the questions pretty covered.
There's one more question. What's the capacity of the aquifer? How long will it take you to fill it up? And when it's full, what do we do then?
So as I mentioned earlier on, this is a very large aquifer. It's about 500 million tonnes, so that will last for a long period. But we've also been looking at a number of other stores in the area. We've identified half a dozen other stores which give us the same capacity again. So we're thinking about how we then grow from this and expand the network to other stores to allow us to capture more CO2. It's worth saying that the UK has one of the world's best geologies for carbon capture and storage. I forget which institute looked at it, but they reckon we've got the world's third best geology for carbon capture and storage. So we've got huge potential in the UK. Bayes have done a fantastic job mapping all the potential stores in the UK, so it's very well known. We've got a real advantage compared to other locations, other geographies.
Okay, thanks very much, Colin. I'd just like to say, Colin, thank you very much for that talk again, and also for David for the project Sofia. Two great projects up in the northeast with a strong Teesside connection, driving the UK towards net zero. So I'd like to thank the presenters and thank all the participants for joining the webinar. I hope you have a good evening. Thank you and good night.
Thanks, everybody.